Class 9 Science, Chapter 4, Structure of the Atom, and in this video we will discuss about octet rule, valency, atomic number, mass number, isotopes and isobars. First come to octet rule. Atoms of elements completely filled with 8 electrons in the outermost shell. Okay, 8 electrons is also known as octet. Are stable and show little chemical activity. That is, presence of octet configuration in the outermost shell show the little chemical activity and they are stable. Therefore, atoms which are not having octet try to achieve an octet in the outermost shell. This is done by sharing or gaining or losing electrons. This is called octet rule. Valency electrons. In the previous video, we have discussed about the distribution of electrons in various cells, and that is electronic configuration. Okay. The last shell or outermost shell is known as valency shell, and the electrons present in the outermost shell or valency cell of an atom are known as the valency electrons. Now, what is valency? Combining capacity of an atom of the element is known as its valency. The number of electrons gained, lost or shared so as to make the octet of electrons in the outermost shell gives the valency. Like hydrogen. Okay, how many electrons are present in the hydrogen? There is a 1 electron in hydrogen. That's why its electronic configuration is 1. Okay, and in case of hydrogen, actually presence of 2 electrons in case of lithium is the indication of stability. Okay, and that is a noble gas, and the nearest noble gas of hydrogen and lithium is helium. That's why again presence of 2 electron is also the indication of stability, and that's why hydrogen its valence is 1. Lithium electronic configuration is 2-1. After losing 1 electron, okay, it achieved the configuration of helium, which is a stable configuration. That's why its valency is 1. The same way sodium, this is 2-8-1. Valence electron is 1, and when this electron is loosed, then this will get the 2-8. That is octet configuration is obtained. That's why its valency is 1. In the same way, magnesium 2-8-2. Valence is 2. Aluminium, okay, this is 2-8-3. Valence is 3. Now, fluorine electronic configuration is 2-7. Now, in this case, how can it achieve the octet configuration in the outermost shell? By gaining 1 electron. That's why its valence is 1. The same way, oxygen electronic configuration is 2-6, and it can achieve octet by gaining 2 electrons. That's why its valence is 2. So we can say valency is equal to number of valence electron, or valency is equal to 8 minus number of valency electrons. Now in case of fluorine, that is 8 minus 7. Okay, this will come to 1. In the same case oxygen, this is 8 minus 6 is equal to 2. Okay, now this table represent the valency of first 18 elements. Okay, I think you can write the valency because we have learned the electronic configuration of these elements. Once again, see hydrogen, this is 1. That's why valency is 1. Lithium is 2. Okay, this is also considered as the completely filled shell, and its combining capacity is 0 because this is stable. That's why its valency is 0. Lithium 2-1. Valency is 1. Beryllium, okay, this is 2-2. Valency is 2. Boron 2-3. Valency is 3. Carbon 2-4. Valency is 4. Okay, number of valency electron gives the valency. Now in case of nitrogen, okay, atomic number is 7. This is 2-5. In this case valency is 3. How? 8 minus 5 is equal to 3. Oxygen 2-6. 8 minus 6 2. Fluorine 2-7. Valency is 1. Neon 2-8. This is completely filled cell, stable. That's why valency is 0. Sodium 2-8-1. Valency is 1. Magnesium 2-8-2. Valency is 2. Aluminium 283, valence is 3. Silicon, okay, this is 284, valence is 4. Now in case of phosphorus, 285. Now two valencies are there. It can achieve octet configuration by gaining 3 electrons. That's why its valence is 3. And it can also achieve the octet configuration if it lose these 5 electrons or share these 5 electrons. Because losing of 5 electron is not energetically favored. That's why this share the 5 electron and achieve the octet configuration. Sulfur, this is 286, valence is 2. Chlorine 287, valence is 1. Argon 288, valence is 0. Atomic number represented as Z. The number of protons present in the nucleus is equal to atomic number. We can say atomic number Z is equal to number of protons in the nucleus of an atom. And as we know, atom is neutral. Okay, that's why this is also equal to number of electrons in a neutral atom. Number of electrons in a neutral atom. But again remember, atomic number is always equal to the number of protons. Okay, we can compare with the electrons because atom is neutral. Nucleons. Protons and neutrons present in the nucleus are collectively known as nucleons. Mass number represented as A. Sum of the total number of protons and neutrons present in the nucleus of an atom is known as its mass number. And as we know, protons and neutrons are collectively known as nucleons. That's why total number of nucleons is termed as mass number of the atom. And we can say mass number A is equal to number of protons, which is also equal to atomic number plus number of neutrons. And with this relationship, which correlates three things: mass number, atomic number, and number of neutrons. Okay, if two things are given, third we can calculate. How can we represent an atom? Now, if symbol of atom is X, suppose X, and its atomic number is Z and mass number is A, then this is written like this. Okay, for example, nitrogen with atomic number 7 and mass number is 14. This is the notation or representation of nitrogen atom. Isotopes. Atoms of the same element. When element is same, definitely atomic number is also same. Atoms of the same element having same atomic number but different mass number are known as isotopes. For example, 3 isotopes of hydrogen. Protium, this is written as 1H1. It means atomic number is 1 but mass number is 1. Deuterium, atomic number is 1 but mass number is 2. This is also represented as capital D. Tritium, this is 1H3. Okay, this is T. You can see that is atomic number is same in all these three. Okay, but mass number is different. In protium 1, this is 2. In tritium 3. Actually, this difference in mass number is due to the difference in number of neutrons. Okay, like isotopes of chlorine. There are the 2 isotopes. This is also known as the chlorine 35 and chlorine 37. Mass number are different. Atomic numbers are same. And again, the difference in mass number is due to the number of neutrons. If you are asked to find out the number of neutrons in chlorine 35 and chlorine 37, then how will you find out? Simply this is 35 minus 70. Okay, and this is equal to, I think, 18. This is the number of neutrons in chlorine and in chlorine 35. And in case of chlorine 37, how many neutrons are present? 37 minus 17, this is equal to 20. Okay, this is another example of isotopes of carbon, that is carbon 12 and carbon 14. Atomic number is same, 6. Mass number is different, 12 and 14. Okay, the chemical properties of isotopes are similar but their physical properties are different. Now just see average atomic mass of chlorine atom. We have discussed that average atomic mass of chlorine is considered or is taken as 35.5. Okay, how this is in fraction? Let us try to find out. Chlorine occurs in nature in 2 isotopic forms, with masses 35U and 37U in the ratio of 3:1. When we discuss the definition of atomic mass, this is taken as average atomic mass. That is average of the masses of its isotopes. Okay, how can we find out this average atomic mass of chlorine? Atomic mass, or we can say that is atomic mass of chlorine 35 is 35, and its abundance ratio, this is 3. That's why this is multiplied by 3. Plus, this is another isotope of chlorine having mass number 37 and its abundance ratio is 1. That's why multiplied by 1 and divide by 4. How this 4? The sum of this ratio, that is 3 plus 1 is equal to 4. If you solve it, you will get 35.5. There is the another way. If this abundance or occurrence of these isotopes in nature is expressed in terms of percentage, that's why we can say this is chlorine 35, this occur in 75% and 37 occur in 25% ratio. Okay, then we can solve this. 35 multiplied by 75, this is the percentage abundance of isotope 35. Okay, chlorine 35. The same way, this is 37 into 25 divided by 100. Why this 100? Because sum of this 75 plus 25 is 100. If you solve it, this is 35.5U. In this way, we find out the average atomic mass of any element. This does not mean that any one atom of chlorine has a fractional mass of 35.5U. Okay, it means that if we take a certain amount of chlorine, it will contain both isotopes of chlorine and the average mass is 35.5U. Applications of isotopes. An isotope of uranium, that is uranium-238, is used as a fuel in nuclear reactors. Okay, this 238 represents the mass number of uranium. An isotope of cobalt, that is cobalt-60, is used in treatment of cancer. An isotope of iodine, that is iodine-131, is used in the treatment of goiter. An isotope of carbon, that is carbon-14, is used in radiocarbon dating. Now, what is this radiocarbon dating? Actually, this is the technique which is used to estimate the age of fossils. Okay, these are the applications of isotopes. Isobars, atoms of different elements with different atomic numbers which have same mass number are known as isobars. For example, this is carbon and nitrogen. Atomic numbers are different. Carbon is 6, nitrogen is 7, but you see mass numbers are same. That's why this pair is considered as isobars. In the same way, calcium and argon. Calcium atomic number is 20, argon atomic number is 18. Different atomic numbers, but you can again see mass numbers are same. Okay, student? Thank you.